Computer networking is an integral part of our lives. We take it for granted until it stops working, that is. In this video, we're going to begin looking at just how computer networks function. We connect computers together to share information and resources. That information may be for work or entertainment. There are many types of devices we connect. Some designed to stay in one place, like a desktop PC, others to be used on the go, like laptops or smartphones. There are also different network technologies to accommodate the various forms computers may take. Whatever the device, in order for it to connect to a network, it must have a network adapter. This is an image of various types of network adapters intended for different types of devices. The first is a wired Ethernet adapter, intended to be connected to the motherboard of a desktop PC. This device is also referred to as a Network Interface Controller, or NIC. This terminology points out the fact that while the entire device acts as an adapter to a network, the actual interface, or the port where a network cable would be connected, is controlled by the chips on the board. The next NIC is also an Ethernet adapter for a desktop, though if you take note of the interface, you'll see it differs from the first one. This adapter is intended for a fiber optic cable, which would be plugged into the rectangular device next to it called a transceiver and slid into the port on the face of the adapter. The third adapter is for a desktop PC as well, though this one provides radio antennas for connecting to a wireless or Wi-Fi network. The last card is also for wireless networks, though it is much smaller than the others in real life and is the kind most commonly found inside laptops, also called a WLAN card, short for Wireless Local Area Network. As I said before, every device that needs to connect to a network must have a network adapter. This is an image of the motherboard of an iPhone 6s Plus, with the chip that acts as its wireless network adapter highlighted in orange. So a network interface is the first component necessary to build a network. The next is a device to process the signals generated by the devices that need to communicate, also referred to as the network hosts. These network devices are what actually create networks. They provide connectivity between hosts by either determining where to send data as in wired networks, or by boosting the signal strength and repeating data as radio signals for hosts to pick up. The first device is called an Ethernet switch. This is the most common type of Ethernet switch, accepting connections over copper cables. There are many other types of Ethernet switches that offer many more ports and even accept fiber optic connections. The next device is a wireless access point. An access point broadcasts and receives radio signals. Hosts connect to the access point and send data they'd like to relay to other hosts. The access point repeats this data so the intended recipient may receive it. You may ask at this point why two devices can't just communicate directly with each other over Wi-Fi. The answer is that this is possible, though it is a separate technology called Wi-Fi Direct. Communicating via the access point has advantages in reliability and security, among other things. This is a cell service tower. This is here simply as a reminder that there are other types of wireless networks beyond Wi-Fi. 3G, 4G, and now 5G are all network technologies as well. The last device is often called a wireless router and is the familiar device we all likely have in our homes, providing connectivity to the internet. A wireless router like this is actually a combination of several devices, among them an access point to provide a connection point for wireless devices and a switch for wired ones. So far, we have the devices, a network adapter, and a device to handle the data sent. The final ingredient is the network medium that will actually carry the data. In the case of wireless devices, radio waves act as the network medium. For wired devices, the most common connection medium are copper cables and fiber optic cables. The connectors that terminate these cables must conform to standards that define their shape and the format of their internal connections. The blue cable at the top is the most common type of network cable. Its technical name is Unshielded Twisted Pair Cable, or UTP. This name comes from the fact that the smaller copper cables that make up a UTP cable are twisted together, as in the smaller image. This twist provides protection for the signals traveling down the wires from electromagnetic interference from the surrounding environment. This hints at a part of the reason behind UTP's name, in that unshielded refers to the fact that this simple type of cable does not contain heavier shielding material like its more robust sibling STP, or shielded twisted pair, which has a metallic foil encasing the wires in addition to the twist. Copper Ethernet cables are most commonly terminated with what are referred to as RJ45 connectors. The correct name for the familiar clear connectors found at the end of Ethernet cables is 8P8C connector, which refers to the fact that they accept 8 conductors or wires. Fiber optic cables, like the orange one at the bottom, allow pulses of light to be used to convey network signals. There are great advantages to this, as light is not susceptible to the electromagnetic interference that can degrade the performance of copper cables carrying electrical signals. This allows fiber optic networks to be very fast and to carry signals over distances measured in miles. If we bring our components together, we form a very simple network called a local area network. This is the most common type of network, so named because it is composed of devices connected in close physical proximity, though that distance may also be much further, as in a large building such as a school. Wireless devices authenticated to an access point also form local area networks. The networks inside our homes are often a blend of wired and wireless devices and allow us to connect things like smart televisions, wireless printers, and desktop PCs that we can access from any room in the house. It's important to note here that although we commonly use the term Ethernet specifically with wired connections, Wi-Fi is also an Ethernet technology. Ethernet is only concerned with how signals are formatted, not the medium they travel over. We will discuss this in a later video. On that note, let's begin to take a closer look at how these components work together. When you have multiple devices connected to a network, how are they to specify where they intend messages they transmit to go? Just as we humans use our names as identifiers, computers must uniquely identify themselves to be able to communicate without confusion. The network adapters that computers use to attach to networks help out here. One of the functions of a network adapter is to provide what's called addressing. You can think of addressing in the same way we think of the physical addresses of homes and businesses. In fact, the address provided by a network adapter is called a physical address. This is the WLAN card we saw earlier. On its front in the red box, I've highlighted its physical address, or Media Access Control Address, or MAC address. A MAC address is a series of 12 characters written in a number system used in computing called hexadecimal that uniquely identifies the network interface of the device. This address has further meaning. The first 6 characters identify the company that manufactured the network adapter. The second 6 are a globally unique value assigned by the manufacturer to distinguish the device from all others produced. The term globally unique means that no 2 network adapters in the world should have the same MAC address. There are questions as to whether this is actually the case. However, all that's 100% necessary is that all devices connected to a local area network have unique MAC addresses to avoid problems relaying messages properly. It can be fun to look up what company manufactured a network adapter. The example image is just a picture I found on the internet. I used a tool located at this link to look up the manufacturer of the device. It's listed as ASCII Computer Corporation. Let's try looking up the manufacturer of the network hardware inside my computer. I'm running Mac OS, so to see my MAC address, I'll open System Preferences, click the network icon, make sure my active network adapter is selected over on the left, click Advanced, and then go to the Hardware tab. Here's my MAC address. Just for fun, let's see what company manufactured my network hardware. I've opened the link to the lookup tool in my browser, so I'll paste in my MAC address, click Find, and there we have it, Apple Incorporated. Cool. Now let's see how the network equipment we talked about actually makes use of the MAC address to handle communication. Here we have a simple computer network composed of 3 computers connected via wired Ethernet to a switch. Switches are actually smart and have memory. A switch takes note of the MAC address of each device connected to it and which port the device is connected to. This information is stored in the switch's memory in its MAC address table and is updated anytime a device connects or disconnects from the switch. When a connected host sends data into the switch, the host includes the address of the device the data is intended for, much as we write the address on mail we send. When the switch receives the data, it looks at the address and compares it to current entries in its MAC address table. If a matching entry is found, the switch forwards the message out of the port that address is listed as connected to. This allows for clean, efficient communication as messages are delivered directly to their intended recipient. But communication is messy, even for us humans. What happens if a host tries to communicate with a device that's not currently connected to the switch, so the switch has no entry for it? In that case, the switch uses its brain. If data enters the switch addressed to an unknown host, the switch performs what's called a broadcast. It forwards a copy of the message out of every active port except the one the data came from, in the hope that if the host is out there, it will receive the data. The hosts that receive data with an address not matching their own simply discard it. Wireless access points function similarly to switches, though there's a major difference caused by the fact that wireless devices do not have a separate connection directly to the access point and must transmit their data over a shared medium, radio signals in open air. When a wireless host needs to communicate, it sends its data addressed to the intended recipient over radio waves to the access point. The access point then repeats that message. Wireless network adapters listen to Wi-Fi radio channels and receive all messages that are transmitted. Just as in the case of broadcasts from wired switches, when a wireless host receives a message that wasn't intended for it, it discards the message. These are just the fundamental operations that make local area networks function. In subsequent videos, we will look deeper into the details and cover more operations until we understand how large networks like the internet function.